So I'm going to work on mapping IR to machine code today. Right now I have this main file which I haven't really touched that much, but currently it has this test for IR where I've got this main function that returns two values. One of them is a constant and the other one is an expression. So right now if I run this, we get all of these virtual registers with all of the values in them. It's pretty close to assembly, and it looks like it should produce the correct answer. So I'm basically going to work on mapping all of these instructions into the x64 machine code by using the generator that I've been writing, over the past couple of weeks, whenever I've had the time. So the way that I'd want to use this is, for example, to say G is x64.newGenerator. Then we could, for example, call g.generate, and I want to be able to pass in the intermediate representation module. So this mod is basically we've passed a file, which I'm calling a module. And that has a list of functions in it that have been compiled into this intermediate representation. And then so this, after it's generated all of the machine code for it, could, for example, return the bytes that it generated into this text thing. So once I've got this text, it would be useful to see what it's actually compiling to. And because we've got the bytes, it means that we can run it through the disassembler. So if I create a command here, so this will be exec command. We'll do NDISASM B64. And then I think if I do this hyphen, I can set the stdin to a new reader. So we can say bytes new reader, pass in the text here, and then we can get the output. So we could say out is cmd combined outputs. And then we could just print it. So we'll do a blank line followed by the string of the text. So in the generator, I'm basically going to need this new generate function. Maybe I'll put it up at the top here. So we'll have function gGenerator. We'll have generate, and this will take in a module, which is IR module, and it will return the bytes. So the first thing I'll do is just reset the text here, and we'll return the text at the end. So the IR module basically has this slice of IR functions. Functions then have a bunch of blocks in them, and then the blocks are filled with these instructions. And the instructions are the things that I'm going to be mapping into machine code. So we can loop over, for example, all of the functions. We'll say function range in mod.functions. And then we'll want to loop over, maybe here we'll say g.generate function, and just pass in the function. So we'll put that down here. So this will be generate function. So this takes an IR function. This one doesn't need to return any bytes. The return of the bytes is just as a convenience, really. So at the beginning of a function, we basically just need to loop over all of the blocks. So we need to range over all of the blocks in the function. And then within the blocks, we need to loop over all of the instructions. And then when we see an instruction, we just want to generate that instruction. So we'll generate instruction, pass in the instruction, and I think that will do for that one for now. So we'll say generate function is generate insta. This will be instruction. Okay, so now in here, an IR instruction basically has an op that we can switch on to decide what to do. So we'll switch on insta.op, and we'll first do the default case. So we'll say in the default case we'll do panic unhandled IR instruction op, and I'm pretty sure we did op has string implemented on it, so we'll just do op.string to print out the unhandled one. Let's just see what I've missed so far. Syntax on main 51. Okay, this should be like that, I think. Okay, generate instruction. Okay, declared not used out. This should be out. Okay, so we get unhandled IR instruction op const. So I'll want to map this const into a mov instruction, for example. So we can say, in the case that we see const, we could do, g.mov, and we need to get the correct size, we need to get the destination, and we need to get the source. So from the IR instruction, we need to map the virtual register IDs into actual register operands. So it would be useful to have a helper in here that's, for example, let's say IR value to operand. So in here we would take a value, which we'll just say is, ir.value, and we're going to return an operand that we can use in the machine code generation here. We'll also need the size, and this will basically be the IR type to a size. So we'll have another function here for IR type to size. So this one's going to take a type, which will be an IR type, and IR type is just an enum, so I don't need a pointer to that. And it will return a size. So we'll just do this one quickly. We'll just say, in the case that we've got IR S8, and I think actually this should be I8, I16, I32, and I64, but I'll fix that another time. In this case, we want to return a byte. Then in the case of S16, we would return a word. Then for 32, we would do dword. And then for 64, we would do keyword. And then in the default case, we'll just say panic unhandled IR value type. We'll do type.string. Okay. And then for the IR value to operand, we basically want to do this based on the kind of the value. So if we get to value here, each value has a kind, and that right now can just be immediate or register. So we'll do a switch on the value kind, and in the case that it's IR immediate, we want to return a new operand that represents an immediate. So we'll do I of value.value. And in the case of IR reg, we're going to want to return something where we figure out a register, for example, AX or whatever. And then in the default case, we'll just do a panic again. So let's just take this one, and we'll say unhandled IR value kind. So this will be value.kind.string. So we can't just return AX for everything. So we'll basically just write a very bad register allocator here right now. So we'll say allocate register. And we'll take in the IR register ID. So this will be the reg ID, which is an int64. And we're going to return an operand from here. So the way I was thinking of doing this, at least initially, is to have a very bad register allocator that will just crash if we use too many registers. And yeah, we'll just go from there. So for example, we could have a map of IDs to the register operands that they're mapped to. So we could say, for example, if reg OK, and we can have this map of registers where we look up the register ID from the IR, and if we've assigned one to this register ID, we just return it. Otherwise, we need to look through some list of available registers that we can use, and just take one of them, basically. So what I'll do for this is I'll just have an array of registers, and we'll just keep an index of where we're looking in the array. And if we go over the end, we're just going to crash. So we'll say reg is, let's say, available registers. And then we'll have some state on here, which is like the next reg index, or the next register index. After we've got that, we'll increase the index and we'll return the register. So we need this available registers array, which we'll put up here. So this will just be a bunch of operands, and I'll just go to the register list here to take them all. And there are a few registers in here that we need to take out. So for example, we don't want to use SP and BP to just store the, just to store general values in. We're also going to be implicitly using AX and DX. So because right now I'm not going to be doing anything like preserving values or anything, we'll take these two out to make sure that they don't, we don't stomp all over the values and end up with an incorrect calculation or something. And then whenever we generate a function, the register map is going to be per function, so we should clear the g.registers, and we should set the next register index back to 0. And then when we create a new generator, we'll just do this registers thing where we say map. We'll make a map of int64 because the register ID will be an int64 to operands. And we'll add that as a field here. So we'll say registers is a map. Okay, so let's just see. We should still let's just see what we've missed here. So we've got next. Okay, yes, I need to add this as a field as well. This can just be an int. And then we've got size, dest, and source. So size, dest, and source here, we can just use the helpers that we've got now. So we'll say this is a g.ir type to size, and for this one, const will only ever have one source and one destination, and both the source and the destination should be the same size. So we'll just pass in the type of the destination here. So this will be the instructions destination, first destination type. Then we'll take the destination. So this is going to be an IR value to operand. And this will be the same thing, we'll just get rid of the type on the end. We need to pass through the whole instruction destination value. And then we'll do one for the source as well, which is, that's in the sources here. There should be destinations with an S. Okay, so that's enough to handle const. So we need add and whatever other ones we've got. So if I go to IR over here, we've basically got const, add sub, moldiv, and ret. So we need to have a case for each of these instructions. Okay, so in the case of add, we'll just copy this down here. So add, as far as the IR instruction goes, add has one destination and it has two sources, which are the left-hand side and the right-hand side. So this is the LHS, and we've got an RHS, which is the other source, and we want a destination to put it into. We'll get the size just as usual from the destination, or as usual as far as const goes so far. And then we'll basically want to call add. But because of the way that the machine code works, the instructions work on x64, we need to move the LHS into wherever the destination is going to be, and then we need to add onto that. So we could say, for example, if the destination does not equal LHS, then we'll do a mov of size into destination. We'll move LHS into there. Then we're going to add, we want the destination register with RHS, because destination will currently have the LHS copied into there, and then we're going to add the RHS onto that, which will become the result in the destination. So we should be able to do a similar thing here for sub, since that works in the same way. Mul and div are going to be a little bit different. So if we go to the documentation for div, let's say, well, let's do div first. Okay, we'll go to div. So we've got div down here somewhere. Here it is. So when it comes to div, it's going to use this dx-ax pair as the dividend. So we need to zero out that those top bits in the dx register before we do the computation. So let's just let's go and do div first down here. So again, this still has the same operands. It's still got a destination, an LHS, and an RHS. So this is all fine. But we need to zero out dx, and ideally what I do here is like an XOR of dx with dx. But I haven't implemented XOR, so we'll just do a mov of dword into dx, and we'll do an immediate of 0 to zero out that those top bits that are going to be the dividend. Then what we'll do is say whatever we move into AX is basically going to be the LHS. So if the LHS is not AX, then we'll mov the LHS into AX. It needs to go into AX for this to actually work, because it's a single operand instruction. So this sets up the dividend for us. Then we can do the actual divide. So we'll do div on, so this is a div of size onto, we've got AX. Oh, this is a single operand thing, so we want to do RHS here. And then what we'll want to do is say that if the destination is not AX, then we want to move into destination from AX. So we want to move the quotient out of AX into wherever the destination is supposed to be. Then for multiplication, this is also a single operand thing, so we'll do a similar thing where we say that if the LHS is not AX, then we're going to move LHS into AX to set up the multiplication. Then we can just do a mul on RHS. And then the same thing down here. If the destination isn't already AX, we move AX out to wherever the destination is supposed to be. For return, we can just do a g.ret. But if we go to look at the IR here, we can return values. So in this case, I'll change this just to be returning a single value. So we'll return this computation here. Oh, undefined add. Okay, I need to put the IR on these cases here. and rets. Okay, so we have a single return now, and you know, in the calling convention on Windows, I'm pretty sure it's the same on Linux as well. The return value should be stored in EAX. So if I ran a command line argument or a command line program and I wanted to see what the return is on Windows, at least I can say echo error level, and this will echo whatever, this will print whatever came back from the program in the EAX register. So when we return, what we want to do, we always want to do the return, of course, at the very end, but we also want to say that if the length of the instruction sources is greater than 0, we'll just assume that we're only going to deal with one return at the moment. So in this case, what we want to do is say, you know, we'll get the source. So this will be the value to operand of source is 0. And then we'll just say that if source isn't already AX, then we're going to want to move dword, because it's EAX, we're going to want to move it into AX from the source. So if I run this now, so now we're printing out from calling the disassembler. You know, we've got this this const 1 up here becomes this mov into EAX down here, and I think I should be skipping EAX though. So next register, allocate register. Yeah, I'm not calling the allocate register helper, so we'll call that on reg ID, which is value.value. Okay, let's try that again. So here we've now got index out of range 12. I wouldn't have expected that to be out of range. That's in allocate register, so that's probably at this point here. We reset it to 0, which is fine. Maybe I'll just remove one of these. We still get 12 here. Okay, that works without that. Okay, so it's basically just because of all these extra mobs and everything in here right now. Okay, I think I'm just going to have to leave it like that for now. But it is generating machine code. So we get a mov of 1 into ECX, that's been used, so now the next one is in EBX with the 2. Then we do an add, which means that we're moving EDI into ESI right now. So I think that there's something wrong here, because we should be moving V1. I think I know what's wrong. Okay. I've just forgotten to update the map, basically, in allocates register. When we get the register, we need to say g.registers reg ID equals the register. Okay, that looks much better. So we're moving 1 into V1, so V1 is ECX, V2 is EBX. Then to do the add, what we're doing here is saying that V3 is, so we've got CB, so we're moving ECX into ESI, and then we're doing an add of EBX, which is the 2, onto ESI. So that is adding correctly. Then we've got the 3 and the 4 here. So it looks like it should all be working okay. We're moving into EAX here for the multiplication. So that's EDI, which is the 3, which is the first, which is V4 up here. So V4, and then V5 is, so V5 has the number 4, which is R8 here. And then after we've moved the V4 into EAX, we use V5, which is R8, to do the multiplication, and then we move the result out of EAX into R9. So V6 is R9, for example, and it looks like we go all the way through just fine. So yeah, it looks like it's creating a, I mean, semantically correct machine code as a one-to-one mapping, even if it is pretty bad machine code. Maybe what I'll do with this quickly is just to check that it's running correctly. We'll do some computation that's not going to end up as like a floating point number. So maybe what we'll do is we'll say, 10 plus 20 divided by 2. Or maybe we'll do, 10 plus 20 divided by 2, so we'll end up with 20 there, minus 5 to get 15, or minus 5 multiplied by 2, so we should end up with 5 at the end here, I think. So let's just run this and get the machine code out. Maybe what I'll do is I'll open up test cases, NASM, and just get rid of these. So here we'll say this is main section text. Global main, I think, is how we do this. So then we'll do NASM f win64. We'll do test cases.asm. So this should give test cases.obj, which I can link. We'll say that the subsystem is console and the entry is main for test cases.object. And then if I do test cases.exe and echo error level, we get 10 here. So we've got 10 here, so 10 plus 10 is 20, and then this is 10 minus the 20 there. So we end up with 10. So it looks like it's correct. So we put the result into EAX, and then I was able to inspect that with echo error level. So that's a quick, very naive, very, semantically correct, but very bad sort of machine code-wise implementation of the IR to x64 mapping. There are quite a lot of directions I could go from here. I could implement a proper register allocator, like the standard way with graph coloring and things like that. I could work on the type checker a bit more, add more to the language, insert optimization passes for, constant propagation, dead code elimination, things like that on the IR. But I think next, what I want to do is not have to rely on NASM and the Microsoft linker to create these executables. So next time I'll probably work on generating an executable file in the PE format, and then dumping the code that we generate into there so that I can run it. And then after that, we'll fix all of the problems with register allocation and all that sort of stuff.